Whenever I mention microwave, most people say, I use that to warm up my leftover lunch, like that. Yes, so microwave oven is probably the first thing come to your mind. So are we really going to cook a cell in a microwave oven? Probably not, okay? And then here at Rutgers, you have the Win Lab, the world famous Win Lab. So you also know that microwave is commonly used for wireless communications. And then as we advance to 5G, we'll move to beyond 28 gigahertz. So we're even moving from microwave to millimeter wave, okay? And then you also are probably excited about self-driving car. But even before the self-driving car is popular, today already many cars have a smart cruise. And what makes the smart cruise and self-driving car possible is a millimeter wave radar, right? So, and the millimeter wave radar is like your eyes can see front, back, and side, etc. And so today you already probably using millimeter wave radar for any collision. So these are the well-known uses. But in terms of biomedical applications, first, there's a popular use for microwave tumor ablation. So you put microwave source at the end of endoscope to burn off a tumor, okay? And this is a minimally invasive. You don't have to cut open somebody's body to remove the tumor. And then microwave tend to absorb more strongly by a tumor because it has a higher water content. So you can more selectively remove the tumor. Microwave or millimeter wave radar to sense the vital sign of a person wirelessly. Okay. Come to our own study. So we, as I mentioned, we did the we also did the very broad spectrum kind of characterization, and then we can extract the capacitance and then the conductance from the measurement, and the capacitance is roughly proportional to the dielectric constant of the material. And you see that by modeling a cell with simple resistors and capacitors in either series or parallel configuration, I mean, this represents electrical engineers' simple view of a cell. We can have these membrane resistance, membrane capacitance in series with the cytoplasmic resistance and cytoplasmic capacitance. Here, we just divide the cell into two parts. One just the membrane, and we call everything else the cytoplasm, as if it's a homogeneous material. This is just the starting hypothesis. But not only we publish later, but also we use very different approaches. For example, after we culture the cells, we resuspend them in basically isotonic solution with very little ion contents. That makes electrical characterization easier, okay? And then, but the sucrose solution is still sufficient to keep the cells alive for hours, long enough for our experiment. And once we culture the cell, we will resuspend the cells in a sucrose solution, and then we'll use microfluidic techniques to pass the cell through a microfluidic channel that's built on top of a coplanar waveguide for the microwave measurement. This is the more detailed picture of the coplanar waveguide designed with two types. One will trap a cell in a series configuration, and the other one will be in the parallel configuration. As you can see, we can change the frequency and power to do trapping, characterization, electro-poration, and finally detrapping. And all this can be done in about a minute. Many biologists, they even though they involve electrical techniques, but they don't know how to design well-matched circuit. So they typically stay with kilohertz and megahertz because there the impedance matching is easier. Okay. And then at this level, we can clearly see the difference whether the microfluidic channel is filled with sucrose or air. And we can use that to calibrate the measurement. But whether we have a cell trapped or untrapped, you cannot see the difference here because the difference is only about 0.01 dB. Okay, so we can only see the difference if we plot the difference separately. Okay, this is the net change. You can see that, especially on the right side, it's down to the 0.01 dB. Okay, and even though the signal can be rather noisy and small, but we can reliably extract the different classes and resistance parameters because you can see that if you vary the resistance or classes, the behavior will change quite significantly. Here we just experimented on 8 live cells and 8 dead cells, and you can see the signals are clearly spread out in 2 clusters, well separated. Okay, and this turns out to be very important because there's no good way to quickly tell a live cell from a dead cell. Traditionally, if you're a biology major, your professors say, okay, you culture the cell overnight, and then tomorrow, if you see the cell multiply to thousands of cells, that means the cell is alive. Okay, otherwise it's dead. Okay, but this is a wonderful thing that electrical engineers can contribute. We can almost instantly tell whether the cell is live or dead. And this is our first contribution. Okay, and we in more detail we extracted the membrane resistance, membrane capacitance, cytoplasmic resistance, and cytoplasmic classes. Okay, and compared to the historical data, all in the kilohertz and the megahertz range, we span much wider range, and we can not only report the average but also standard deviation. Okay, all the others they just throw some number down, and if you recall, only reliably determine the value of the cytoplasmic capacitance at gigahertz or higher frequencies. So how these people tell the cytoplasmic capacitance just based on kilohertz to megahertz measurement. Can you guess? May I ask? Thank you so much. I'm very encouraged that you would try to venture a guess. Yeah, you'll find that many questions in research you can just apply your common sense and try to, like you did, you try to venture a guess. Okay. So in conclusion, I think first I mentioned that we use a lumped equivalent circuit with non-dispersive resistances and capacitances, and that can model the different relaxation mechanisms without having to resort to dispersive permittivity. And then we expand the frequency range going up to gigahertz, and we extract the cell characteristics that compare well with traditional dielectric spectroscopy in the kilohertz to megahertz range, but it should be more accurate, and also especially regarding the cytoplasmic capacitance. And this approach is now being extended to be more complicated structures, and then even wider bandwidth, and then we can more reliably determine the subcellular structure, not just the cell as a whole. Okay. And finally, I'd like you to remember a microwave signal can be fast, compact, label-free, and low cost for separating light from dead cells, and hopefully from normal cells from cancerous cells, and then as well as reversible and irreversible electroporation.